Alright, here we are for the last part of today's lesson, and this will be continuing on more material from Chapter 14 from the Bioreactor Mechanics book for ENGR 2302, Engineering Dynamics. Alright, so now I'd like to look at the impulse momentum theory as applied, the impulse momentum principle as applied to systems of particles. So the impulse momentum system as applied to systems of particles. Here. So impulse momentum principle, systems of particles, etc., etc. So let's consider a generic system. So I'm going to write a few axes here. So same axes, I'm not using local axes anymore, all global here. Origin x and y, origin x and y, x and y, and the origin x and y. Origin x and y. And then if I draw three dots representing three particles, so I'm going to have particle 1, 2, and 3. Or maybe actually A, B, and C. Let's do A, B, and C. So here, each would maybe have its own velocity. Each would have its own velocity. And if I wanted to look at the momentum, if I drew out not the velocity vectors, but the momentum vectors, the momentum for this one would be MA, VA at point 1. So this is going to be position 1 and position 2. So basically we're going to have a plus and an equals, and this is position 1, and this is, or I should not say position, but moment in time 1, moment in time 2, plus something, so the state at 1, the state of momentum at something 1 plus something that we'll see will equal state 2. So plus MBVB 2, or sorry, MBVB 1, and then MCVC 1. So this is particle A, B, and C, and these are just very general things. All I'm doing here is just showing this in a very general system. And what I might apply to this system is a combination of forces and moments. So maybe a summation of moments from T1 to T2, or a summation of integrals of moments. So we have a summation of an integral sign, isn't that lovely? T1 to T2 of the moments, any moments occurring about the origin, and integrating across dt. And I also might have some forces. And so I would have also a summation of the integral of the forces, T1 to T, from T1 to T2, of F dt. So basically we'd be integrating across all the forces and all the moments, and that would produce the final the final velocities of all of these systems. So basically we're saying that across a length of time, the forces and momentum applied to a system over a period of time, the summation of forces and moments applied to a system of particles over some length time, T1 to T2, will produce a change in the state of the velocity. So if I had something like this here, A, B, and C, and the momentum here would be something like MA VA2, MAVA2, or sorry, yeah, MAVA2, not M2, MAVA at point 2, then maybe, and these don't have, I mean, the directions of these are not important. This is just we're talking in general terms here. MB, VB, so I'm going to draw this out and then work through some of the math on here. And then MCVC at point 2. So let us look, I want to look at the conservation of linear and angular momentum. The angular momentum is going to be affected by this term, and the linear momentum is going to be affected by this term. So building on what we saw yesterday, the summation of forces will be equal to the rate of change in momentum, in linear momentum, L dot. And also, the rate of the summation of the moments will be equal, or moment vector maybe, will be equal to the rate of change in the angular momentum. The rate of change, so H dot, the rate of change in the angular momentum. And then the forces, replacing this, would be, if I take this in terms of time, I would have the summation of the integral T1 to T2 of F dt equals L2 minus L1. So instead of looking at a rate, if I integrate this across time, the rate just transforms into a change in angular or linear momentum. And I can do the same here, integrating. So summation of from T1 to T2 of MO dt is equal to no longer the rate of the change in angular momentum, but simply the difference in angular momentum between T2 and T1 minus T1, or sorry, minus H1. Then I can say that, so finally, I can say L1 plus summation of the integral, so really what we're seeing here, plus summation of the integral of T1, from T1 to T2 of F dt equals L2. Just moving this over here. And the same idea here. H1 plus the summation of the integral from T1 to T2 of MO dt is equal H2. Is equal to H2. Is equal to H2. Okay? Okay, so then let's look at an interpretation of this. So, the momenta, plural of momentums, or plural momenta, plural of momentum, the momenta, that's a cool word, that's a very nice, interesting word, of the particles. The momentum of the momenta of the particles at time t1, T1, and the impulse of the forces from T1 to T2 form a system of vectors equipolant to the system of momenta, the system of momenta of the particles at time t2. In other words, they are vectorally equivalent, they are momentum equivalent, energy equivalent, etc., of the particles at time t2. So the momentum of the momenta, not momentum, the momenta of particles at time t1. Let me clean that up a bit. And the impulse of the forces from T1 to T2 form a system of vectors equipolant to the system of particles at time T2. At time T2. Okay? All right, so with that, I think that's most of the theory I want to cover. Now I'd just like to work through a few example problems, perhaps maybe 1 or 2 example problems. All right. Okay. So I'm going to work through an example problem. So let us say, this is going to be an interesting one. I have a trolley on a track, frictionless track, and there is a trolley on this. So this trolley can roll back and forth. I'm going to call this A and B. And hanging below the trolley, so this trolley can, maybe it's on a ledge or a rail or something like that, but hanging from it is a cord and a mass. So, let's see. This is mass B or ball B. The cord length is going to be L. The cord length is L. And while cord is at rest, the ball is given a velocity v naught. So, cart A is free to roll. Roll horizontally. While A at rest, ball B is given an initial velocity, if I can manage to spell initial properly, and what was that? Was that? Given an ideal, given an initial, an initial velocity, v naught, I should say, v naught. And this is going to be, I'm also going to say v naught equals the square root of 2gl. So it's given a velocity equal to the square root of 2gl. And so all this is given. And this has mass ma. This is a variable problem. And mb. And I want to find the A, the velocity of B as it reaches its maximum elevation, and B, the maximum vertical distance ball B will rise. Ball B will rise. So the basic idea is that this thing is going to swing back and forth. Now, if this cart were just fixed to the ground, this wouldn't be a big deal. This wouldn't be that difficult. It would just be a very simple, idealized, simple pendulum problem. However, we have made things more difficult by making it so that the support of the pendulum can now roll backwards and forwards. Uh-oh. See, here's the thing. This thing starts out with initially, this cart has no horizontal momentum, but the ball does have some level of horizontal momentum, right? The ball has a horizontal momentum, and if it's going to swing up, which it has to if it's moving to the right, the ball has to swing upward, right? If it's going to do that, in order to swing to the right, as it swings higher, its horizontal momentum by necessity has to decrease because it can't move. It can only move horizontally when the cord is fully stretched out. So the velocity has to go something like this. And in order to do that, if the ball B must lose some of its horizontal momentum, and but still the total horizontal momentum in the system must be conserved. So we'll have to model this and figure out how this works altogether. So I'm going to model this first by creating a system of free body diagrams. All right. So solution. First, I'll create a system of free body diagrams. Here. So horizontal momentum is going to have to be conserved. We know that. So let's say we have hanging from this a weight. The weight. Initially we have momentum, ma v naught, v naught. Then plus something like this, plus any horizontal forces any forces that are going to be on the system. So the only forces acting on, basically I'm going to draw out any external forces on the system. And the only external forces acting on the system are vertical forces. So what I'm doing here is, look, I'm coming back to this. The initial momentum plus any forces, the integration of any forces, must equal the final momentum. I'm applying the impulse momentum theory. So this is the initial momentum plus any forces, and these forces are going to be, let's see, well, the forces, they're all vertical. This is going to be weight B. Well, these aren't really free body diagrams, I should say these are more impulse diagrams. So weight B times T. Weight B times T. These are forces times time. Will yield, and then over here, I will have weight A times time. And then upward here will be R, the reaction, times time. Or F normal. I like F normal better. F normal times time. The normal force times time. And so this then must equal the final momentum. So basically this is initial momentum now for constant forces, the reason I have these times here is that if for a constant force, the integration of that with respect to time is just the magnitude times time. So this is the integration of forces, of external forces, equals the final momentum. And if I then draw this out, well, what do we have? This thing will be moving something like this. And this is MB times VA. MB times VA 2. And then MA times VA 2. Actually, let's probably say MB. Sorry about that. MB VB. I believe, yes. MB VB. Well, let me think about that. Let me think about that. Actually, no, that does make sense. VA2. And I'll explain why. MA. And this would be, if I don't erase my lines. This would be MA VA 2. Okay, so what this basically says, what I'm doing on this, what I'm at the point where the pendulum is at its highest height, at the point when the pendulum is its max height, it is basically stationary with respect to the support, right? Wherever the pendulum is going to be at its max height, it's going to be stationary with respect to the cart. So where pendulum is at max height, it is stationary with respect to the cart, aka it is co-moving with the cart. Thus, at max height, both will have velocity VA 2. VA at 0.2. Okay. So let's consider that then. Here. Okay, again, all of this is going to be based off of the simple conservation of momentum, or impulse momentum theory. L1 plus the summation from T1 to T2, T1 to T2 of F dt is equal to L2. Is equal to L2. And I could also draw out something like this. Let me also draw another diagram to illustrate this idea. The balance of momentums here. So AB and here have velocity, something like that, except it's going to be equal to 0. So here, VA at 0.1 is equal to 0, and here VB at 1 is equal to the V naught that we saw earlier. The V naught we saw earlier. So this again is position 1. I'm just reinterpreting this a little differently. And position 2. Position 1, position 2. And the cart now has velocity of VA2. Of VA2. And ball, the pendulum, also has velocity VA2. Or in other words, also has velocity VA2, so you have velocity here, but VB at 0.2 is equal to VA at 0.2, and velocity of V with respect to A, or sorry, of A with respect to B is 0, or at 0.2 is 0. So the normally there is a tangential component to the velocity here, and it would be every point between here and here. But at this point of maximum height, the ball and the cart are not moving with respect to each other. Okay. All right, questions on that? Okay. So what I'm going to do is I'm going to set up a balance of momentum based off the x direction. So set up balance of momentum. On horizontal axis, or x-axis. And this, actually, maybe I'll do that on the next slide here. So again, the balance of momentum based on the x-axis, I have MA VA at 1 plus MB VB at 1 equals MB, or sorry, MA, VA, or MA, VA at 2 plus MB, VB at 2. And you might be asking, wait, where are the forces? Well, this equation works. The external forces applied to the system in the horizontal direction are 0. Applied in the horizontal direction are 0. Horizontal direction are 0. Thus, it will simply be a balance of momentum. I don't need any forces in there. The momentum itself is the only thing present. So, velocities at 1 and 2. So, velocities at 1 and 2 are at points 1 and 2. Well, I know that VA at 1, VA, comma 1 equals 0, VB, comma 1 equals V naught, and VB2, VB at 2 equals VA at 2, plus the relative velocity of B with respect to A at 2, comma 2, B with respect to A at 2, equals VA at 2. Again, because velocity of B with respect to A at time 2 is 0. So this term just goes away. Velocity of B with respect to A at point 2. And so then I can have M BV naught equals MA plus MB times V of A at point 2, or simply VA, velocity of A at point 2 is equal to VB at point 2, which is equal to MB over MA plus MB times V naught. And that would be our final result. Well, that would be one of our final results. I want to go a bit further if I want to get the answer for part B here. So we've gotten this here, this part here, the velocity at B as it reaches max elevation. So we've solved for that already, but we now need to solve for the max height. So we now want to solve for the max height. So I'm going to use the same positions as before. So we're going to have a conservation of total mechanical energy. So here, conservation of energy, energy. Well, we'll state that T1 plus V1 equals T2 plus V2. We have no non-conservative forces in the system. When the ball was initially given force, or given momentum, that would be some sort of non-conservative force from the point of view of the system, not from the universe, but from the point of view of the system. But once the ball is moving, energy is just being transferred back and forth between potential and kinetic. It's not actually losing any energy itself. So let us look at the energy breakdown here. At position 1, the potential energy well, V1 is simply MA G times L. So that's the potential energy, the only potential energy. The kinetic energy, is T1 equals, so I'm basically defining where the ball is initially here, the initial lowest point of the ball, this is our datum line. This is, when I say a datum line again, what I mean by that is the elevation that we're forming all of our gravitational potential energies off of. So I'm defining this as the 0 potential energy line, which is why mass 1 has potential energy at point 1, because it is basically L, up height L from our datum. And however, if I were going to have the datum here, I would actually need to give my my potential energy a negative value for the ball here. So T1 then equals 1/2 mb v naught squared, and then at position 2, potential energy well, we will have V2 equals, well, now each of these items, or each of these objects will have a certain amount of potential energy. So MA, and when it swings up, I'm going to define this as height H, the height that it swings. So MA GL, that's not going to change. MA times G times L, plus B plus MB times G times H. Then at point 2, we'll have a kinetic energy. T2 is equal to 1/2 times MA plus MB times VA, 2 squared. All right. Now I can just plug and chug and see what we get. So let me substitute these T1, V2, T1, V1, so V1, T1, V2, T2 into our previous expression here, our balance of energy. I get 1/2 mb v naught squared plus ma times g times L is equal to 1/2 times MA plus MB times VA 2 squared plus MAGL MAGL here plus MBH MBGH. All right, so let's see, how might we work through this then? Well, if you do all of this and you solve through, well, if you work through this, cancel terms out and solve through, you will find, so really the only one we want to isolate is H. Everything else is on, there's only one term that has H in it, so if you work through, cancel out, combine terms, etc., you will find that H is equal to MA over MA plus MB times V naught squared over 2G. And that is a final expression for the height of the maximum height of the pendulum ball in terms of the initial velocity, G, L, length, etc. All right, so maybe one more example problem, and then I think I might let you out a little bit early if we have the time, as long as there are no objections.
I paid for 3 hours twice a week.
Oh, okay then. Yeah. Oh, well,
Hopefully nobody takes it too seriously.
okay. Very serious people here. Okay. So, I'm going to have a pool table. Or a table if you prefer. a pool table. So let's see here. So basically, ball A, I'm going to draw it, but first I'll label this, is going to strike ball V and then ball C. To strike both ball B and C, and then C. A V naught is going to be 10 feet per second. B and C initially at rest. Okay. So let's draw this out. Here. I have ball A with an initial velocity of V naught. It is going to strike ball B obliquely, which just means, of course, as we've discussed, an angle, etc. And ball B will hit at B prime. We'll hit here at, it ends up with a VB, and it strikes the wall at B prime, which is 7 feet from the bottom left corner. So this is the location where this strikes the wall is B prime, which is a distance of 7 feet from the left corner, left bottom corner. 7 feet. Then the initial position here is 2 feet. And let's call this point D. And up here, I cannot draw dimension lines. Up here, we are at 3 feet. Up here, we're at 3 feet. Then, at some time later, some short time later, there is a collision, and we'll end up with A. So it strikes like there, then it goes up here. And A ends up going up like perfectly vertical, and C ends up going perfectly horizontal. So VC and VA. So this one goes straight up, this one goes straight to the right. And then I'm also told, for whatever reason, the dimensions here. This is going to be point A prime and point C prime. From here to here, from here to here is 8 feet. And for here to here is 2 feet. All right. Now, assuming, so again, the ball was here. This is not here. They were both originally here. And then this one goes here, and this one goes up here. Also, collisions are perfectly elastic. And find the velocities VA, VB, and VC, which the balls hit the sides of the table. Of the table. Which the balls strike the side of the table. All right. So basically, how to look at this? Well, we have 4 unknowns, VA, VB in both the X and the Y, and VC. And so we're going to need to find 4 equations and to solve for these 4 unknowns. See, we don't know the location of this initial impact. I just know that VB initially landed 7 feet over. We don't know the length of this part here, but we do know that that VC is purely horizontal and VA is purely vertical, but VB has some X and Y components, so we'll have to solve for each of those. Each of those is its own unknown. So solution, find unknowns, find unknowns VA, VBX, VBY, and VC. All right. Okay, so we're basically going to set up, since we need 4 equations, I'm going to set up, let's see, I'm going to use linear momentum, angular momentum, and energy. I have 2 equations of linear momentum I can use, X and Y. I have an equation of angular momentum I can use, and I can use 1 equation for energy. So all of these are going to be, I'm going to set up equations for each of these and then solve them simultaneously to get our final values. Okay, so let's consider this. Well, I again know that VA is equal to VA O times J, which will be the Y component unit vector. VB is equal to VB comma X times I plus VB Y times J, and VC is equal to VCI. All right? And then if I look at compare momentums, or momenta, draw momenta, initial and final. Initial, I had a single particle or single object, a distance 2 feet up. So yeah, I did label that, good. 2 feet up, which had well, this is ball A, and it had a velocity or a momentum of mv naught equals m, and all of these balls will have the same mass m times 10 feet per second. Then the final momentum well, there's a whole series of momenta here. I'm going to have B here, B with MVB, which has components MVBX and MVBY. And MVBY. Then I would have at A, I would have A and B, or sorry, A and C. I would have MVA and if I can not change the page, I would have momentum MVC. MVC. Again, all of these balls have, all these billiard balls have the same mass m. And we weren't, even though we were given numbers, we weren't given the mass. And since we're trying to find a velocity, it's kind of a good hint that the mass will probably cancel out. So this is then, also as a reminder, this is 8 feet, this is 7 feet, may be useful. 3 feet. and this is 7 feet. Oh, I didn't label that here. That should be 3 feet I had earlier. Or later, I should suppose. 3 feet, there. Okay. So this is our overall state of momentum. So that's our overall state of momentum. And shortly thereafter, on the next slide, I'm going to start working through some equations. Again, I'm just drawing out all the momenta. I'm going to work through them and use them to provide multiple equations I need to solve for the any unknown forces, unknown velocities, the 4 unknown velocities. Okay. First, I'm going to look at momentum, the conservation of momentum and energy equations. Let's look at the conservation of energy, momentum. Well, this is all again L1 vector plus summation of the integral of f dt plus equals L2. And so mv naught, I can set one up for the x direction. Sorry, mv naught. So this is, let me do one for the x and the y. X, mv naught. So we don't have any external forces, so this part is going to be 0 here. Equals mvb, comma x, plus mvc. So the initial x momentum is going to be equal to the x momentum of b plus the momentum of particle c. And then in the y, I can have 0 equals mva minus mvb y. All right, then I can find the momentums here. Sorry, then I can look at angular momentum. I can find the momentums. Now I can look at the angular momentum. In other words, h naught, the momentum about 1, so the momentum at the origin at point 1, h naught 1, plus the summation of moments, summation of the integral of moments, dt, is equal to the angular momentum at point 2 about the origin. So this is why I have all of those, all of the distances, all the labels. See, I'm going to basically be doing a sum of momentums, or really to a certain degree a sum of moments about the origin, about the bottom left corner. See, I basically have a distance from the center, this is point O, a distance from there, well, this is point D, not point O, it looks too much like a D. I have at the point of impact, B prime, I have a certain distance from the center plus the moment arm. So this is then going to be negative 2 feet, moment arm of negative 2 feet times mv naught equals the final state. So this is the initial angular momentum we have, times 8 feet times mva, the momentum, minus 7 feet times mvby, and then minus 3 feet times mvc. Then a final equation. Here, then the balance of energy. The balance of energy will be 1/2 mv naught squared, or it's actually, let me do an intermediate steps first. Will just be T1 plus V1 equals T2 plus V2. And then putting in further terms, 1/2 mv naught squared equals 1/2 mva squared plus 1/2 m vbx squared plus vby squared plus 1/2 mvc squared. Isn't that fun? Lovely. Okay, so we basically have all of you have the angular momentum, the linear momentums, and the balance of energy. So solving the first three equations for VC, well, we get that, or sorry, not for VC, in terms of VC, well, I can get that VA is equal to VBY VBY equals 3VC minus 20. 3VC minus 20. And then VB comma X is equal to 10 minus VC. So then I want to substitute these two terms into the energy equation. Substitute energy equation. Well, I will get that 2 times 3VC minus 20 squared plus 10 minus VC squared plus VC squared equals 100. I can get the quadratic 20 VC squared minus 260 VC plus 800 is equal to 0. And from this, I can find that VA equals 4 feet per second, VC equals 8 feet per second, and VB is equal to 2I minus 4J, or 2I, minus 4J feet per second, or VB, the magnitude of it is 4.47 feet per second. And that there would be our final result. Just set.
You always solve like the linear and the angular and the balance.
Yes, you solve linear, angular, energy, and then balance. Really, you're just using you're asking yourself, what tools do I have in my toolkit, and how might I use this to solve for my system? Really, that's all it is. Okay, well, if there are no other questions, I think that'll do it for this time. I'll see you all next week for more lovely lessons in ENGR 2302. Thanks for watching, and as always, thank you.